All right, so in this video we are talking about measurements, and we are also going to look at several problems that have to do with measurement. And so by the end, I want us to be able to describe and utilize different types of measurements, and also talk about the scientific method, distinguish between a law and a theory, and in the end convert units. When we talk about measurements, usually we focus on two systems. The system that we use in this country is the English system, which is shown here, and then other countries use the metric system. Usually when we do scientific work, we also use the metric system because it is the system that is recognized all over the world. Now, when we talk about the metric system, we focus on what we call international system units, the SI units. The SI units are based on the metric system, and they are derived from these metric system. So the SI units, we have two types of them. We have what we call base SI units and derived SI units. So among the base SI units, we have 7 of them. So they are given in this table. You just need to study this table to learn about these units. So we have units for mass, which is a kilogram. We have unit for length. We have unit for time, temperature, electric current, amount of substance, luminous intensity. So these ones are base SI units because you don't need to multiply them with anything to give you a unit. A kilogram is just a kilogram. A meter is just a meter. A second is just a second. A Kelvin is just a Kelvin. You don't need to multiply things to get to a Kelvin. So these are known as fundamental or base SI units. Then we have derived SI units. So these units are obtained by multiplying or dividing base SI units. As a reminder, we know that we have only 7 base SI units, but we have a lot of derived units. In this case, we just have a number of them. So like force is a derived unit with a symbol F, and the unit has a symbol of N standing for a Newton. But to get to a Newton, you need to multiply mass, that is in kilogram, times length, that is in meters, and then divide that by time in seconds. And because a Newton is obtained by multiplying and dividing, the Newton is a derived unit. So it's the same thing for volume. The unit is a cubic meter. It is a derived unit. Um, Another form of volume is a liter. So a liter is the same as a cubic decimeter. That is also a derived unit. So we can say that we have a lot of derived units, but these derived units are obtained by multiplying or dividing base SI units. However, both the base and the derived, both of them are SI units. Now, there's this important derived unit that we look at. It is called density. What density does is just measure how packed the particles are in a substance. So it measures how packed the particles are in a substance. So here, if this is substance A, this is substance B, we can see that substance B has higher packing of the materials. As a result, it is going to have higher density. So B has higher density than A because particles in A or particles in B are higher packed, are more packed than the particles in A. And the density has a formula. So the formula for density is mass divided by volume. So it just tells us that the more packed the material is, the higher mass it has per a specific volume. One thing we need to take note is that density must always combine mass and volume. You cannot use mass only to tell you the density. You cannot use volume only to tell you the density. Density must have both mass and volume. So we need to take note of that. How do we use this calculation, or how do we use this formula? Let's look at an example. So if you want to determine density, as we already indicated, you need to know the mass and you need to know the volume. So you need to measure the mass. So here we are measuring the mass. And you need to determine the volume. Volume can be determined in two ways. It's either you just measure using a ruler. If you are measuring a regular substance, like if you have a substance that has a regular shape, like this one, you can just measure the length, height, and width. You get volume from there. So you say the volume is equal to length, width times height. So you can obtain the volume by using a ruler. But if you are dealing with an irregular substance, like this rock here, you can determine its volume by difference. So what it means is you have your water, you have initial volume here. So I say volume 1. Then you add the rock into this water, and then there's the change in volume. So this is volume 2. So to determine your general volume, you just subtract the two volumes. So that is determining volume by difference. Once you are able to determine the volume and determine the mass, then you can use that information and plug in. You can take that information and plug in into this formula. Density is mass divided by volume. Let's look at an example. So we have a rock weighing 15 grams. We drop this rock in water and we see an increase in volume by 4 milliliters. So what is the density of this metal? So as usual, we go with the formula. Density is mass over volume. But our mass is 15 grams. Our volume is 4.0 milliliters. This tells us that our density is 15 grams divided by 4.0 milliliters, which gives us 3.8 gram per mil. So we need to know that the units for density, at least for this class, are grams per milliliters or grams per cubic centimeter. We'll see why. So that's how we determine the density of a substance. Let's go to problem number 2. 15.75 grams of an unknown metal displaced 1.50 milliliters of water. We can identify this metal as, so if you have a question like this one, what they are looking for is that you need to determine the density and compare the determined density with the given density and see which of the three, A, B, and C, has the same density as the one we are going to calculate. So for this problem, so I just say solution. So the first thing you do is calculate density first and then compare. Calculate density, then compare. So we'll say D is M over V, which is 15.75 gram divided by 1.50 milliliters, which gives us 10.5 gram per milliliter. This density compares with silver. So actually, we identify our metal as silver. What is important in terms of density is to be able to play around with the formula. You should be able to play around with this formula here. It's an important formula because I can ask you to determine the mass. So mass is density times volume. Or I can ask you to determine volume. And volume is mass divided by density. So you should be able to play around with this density volume. And it's important because you are going to meet similar problems on exam 1 and your final. Now let's move on to a new term, uncertainty in measurement. Usually when we do a measurement, we want to be confident that our measurement is correct. That's what we want. We want to be confident that the measurement we are making is making sense and the measurement is correct, and we are confident that this measurement is within this specific range. Now let's look at 3 rulers. So this is ruler A, B, and C. What is different among these rulers? The answer is the smallest divisions in the rulers are different. For ruler A, the smallest division is 10. So let's say these divisions are centimeters. So for ruler A, the smallest division is 10 centimeters. Ruler B, the smallest division is 1 centimeter. Ruler C, the smallest division is 0.1 centimeter. So we can see that these rulers are different. And another question is, which ruler gives you more confidence when you do a measurement among the 3 rulers that we see here? So in my case, I would go with the ruler that has more divisions or that has smaller divisions than the one that has the biggest division. I will not go with this one. I will not go with this. It will not give me a lot of confidence, but I will go with C. C will give me more confidence. It will give me more confidence that I am measuring the object or my object more accurately than if I am measuring it with ruler number A. And what it means is I am more certain with my measurement when I use ruler C than when I use ruler A. That's what it means by uncertain. I am the confidence of your measurement. Now, mathematically, how do we talk about uncertainty? So we usually talk about uncertainty by showing the range you can give for a specific measurement. Let's take an example of uh, ruler number A. Let's say I want to measure a point just here. I want to measure this point. And what do I say? I'll say this point, I may decide maybe this point is just after um, I may decide this point is, let's say, 7. I'll say this point, I may decide this point is 7. And then someone asks me, all right, you say it's 7, but what is the uncertainty of this point? You mentioned that it is 7. Now, to obtain the uncertainty of this point, you go to the smallest measurement that you get. In this case, my smallest measurement for this one is 10. Or you go to your smallest division. The smallest division is 10. And then you divide that smallest division by 10. So I'll say my smallest division is 10. I'll divide this 10 by 10 to get 1 as my answer. Which means this 1 is my uncertainty. So 1 is my uncertainty. And to show this uncertainty, I will say this measurement is 7 plus minus 1. What does it mean? It means this measurement can be between 7 minus 1 and 7 plus 1, or between 6 to 8. So what I'm saying is I am certain that the measurement that I have made is within this range, because my uncertainty is 1. But as you can see, that is a crude measurement, very crude measurement. Now let me move down to B. I have a point at a similar position. Now I want to determine my uncertainty using ruler B. What do? I still go to the smallest division. So here the smallest division is a 1, because it's 1 here, 1 plus 1, 2, plus 1, 3, plus 1, 4. So the smallest division for this measurement is 1. Now, if I want to determine the uncertainty of this, I'll just take 1 divided by 10, which is 0.1. So my uncertainty there is 0.1, because 1 is my smallest division. Now I want to determine this point, what this point is. You can see here we are moving from 7 to 8. Somewhere here is 7.5. Somewhere here is 7.5. This point may be 7.7. So let's say this point is 7.7. Now I'll just add my uncertainty. Plus minus 0.1. So what does it tell me? It tells me that this point is between 7.6 and 7.8. So now you can see that as we increase the divisions, or as we reduce the size of the divisions, the uncertainty is decreasing. Here the uncertainty is in ones. Here the uncertainty is in 0.1 centimeter. And B is more accurate, or more accurate in terms of measurement. B is more accurate than A. Now let's take the same measurement, but now we put it here. And see how it works. Now for this one, the smallest division is a 0.1. The smallest division is 0.1. So you just divide the 0.1 by 10, and then you get 0.01. That will be your uncertainty. Now, if I have to make a measurement here, I know that I will have a 7. Then I'll count here 0.1, 2, 3, 4, 5, 6, 7. So I have 7.7. But then this is between 7.7 and 7.8. So I can decide what it should be. Maybe I'll just say 7.75. Then once I do that, I'll just add my uncertainty there, plus minus 0.01, which means my value is between 7.74, 7.76. Now I am even more accurate when doing a measurement with C than when doing a measurement with B and A. So usually, if you want more accuracy, you want more divisions on your measurement. Now, uncertainty is important. If I look at a number, I'll tell you which of the figures from the number are certain and which of the figures are, or which figure is uncertain. For example, ruler A. Ruler A, our value was 7. Ruler B, our value was 7.7. Ruler C, our value was 7.75. Now the question is, these measurements, which numbers are certain? So I will say ruler A has no certain value. The reason is we don't know that it's 7 because it's between 6 and 8. So we are not certain whether it's 6 or we are not 7. We are not certain that it is 7 and we are not certain that the value is 8. So this value here, 7, is uncertain. Ruler B. Ruler B, the first 7, this 7 is certain. So for this one, the first 7 is certain. The second 7 is uncertain. So what we are saying is we know, we are sure that it will be 7. We are sure that it will be 7. That's why we have 7 here and we also have 7 here. So we are sure that we are going to have a 7 in that number, the first value. But the second value, we are not sure. It may be 7.6. We may have 6 here. We may have 8 here. Or we may have 7. So this last number here is uncertain. We are not sure about it. We just put it there, but we are not 100% sure that it is a 7. It may be a 6. It may be an 8. For C, the first two numbers are certain. The first two numbers are certain. So only 7 and 7 are certain. The third number, which is 5 here, the 5 is uncertain because it may be 4, it may be 6, or it may be 5. So what we are saying in simple terms, when you are given a number, like if I give you a number like this one, 285, this last digit is uncertain. These two digits are certain. I give you another number like 25.834, last digit uncertain. All these digits before the last one are certain. So we need to take note of that when doing measurements. And another thing, if I give you something to measure, like if I give you a ruler, let me just put it again, A, B, C. If I give you a ruler like this one and say measure that point, for that ruler, I immediately you need to know that you need to measure to 1 decimal point or 1 decimal place. You need to indicate that, okay, here I have 7.4. You need to measure to one decimal place because you put the smallest measurement and the uncertain number. If I give you here, if I say I want you to give me a measurement here, I want your answer to 2 decimal points because first you are going to have 7, that is from here, and then you are going to have another 7 from here. But you also need to indicate between this and this. You need to give me the value. So I would say 7.7, 7.73. So the number of decimal places that you give will depend on the measuring instrument. If you are measuring using ruler A, I don't want any decimal point because this one, the uncertainty is 1. So you can just say this is 7. This measurement you cannot have 7.5. That's impossible because it doesn't allow you to give this one a decimal point. So we need to take note of that. So this is an example of how you use a ruler. So for this one, if I want to make a measurement, I know that I have a 1, and then I know that I am certain that I have an 8 here or a 0.8 here, but then I'm going here. So I'm really not certain about that part. I can just decide to put any number. For this case, I decided that I'll put 4. But then I add the uncertainty, 0.01. So what it means is that the last number can be 0.4, 0.5, or 0.6. This is the uncertain number. Here, this is the uncertain number. That is the last number. So that's what uncertainty means in measurements. Now, if you are weighing something, like you are using a weighing balance, a scale to measure something, you can see that this scale is digital. So it has 1, 2, 3, 4 digits. The 3 digits we see here are certain. This last digit is uncertain. So it doesn't have to be a ruler. No. Every last digit of a measurement is uncertain. That's why when you do a measurement, you see that most of the time your scale, the last digit is changing. Don't worry much about that. The last digit can be anything, but worry about the digits that are inside, the certain digits. So one important thing, when you are in the lab and you are doing what we call titration and you are giving me values, you use a burette you learn more about this burette. Based on the calibration of the burette, I will always want you to give your values to 2 decimal points because of the same issue of uncertainty. So we'll learn more about using burettes in the lab. But we need to take note that I will need 2 decimal points. Let's move on to something else. Important terms that we use in chemistry, in measurements, are accuracy and precision. So, by definition, accuracy is agreement of an experimental measurement of an experimental measurement to a true or accepted value. So, for example, if you have a a bag of peanut or something like that. So you have a bag of peanut, and then the bag of peanut reads 5 calories. And then you get these peanuts and say, I don't trust that this bag is 5 calories. Let me make a measurement. And you make a measurement, you find values 4.9 calories, 5.2 calories, 5.1 calories, 4.9 calories. And you calculate the average or the mean of this, and you find that it is maybe it's not the true value. Maybe it is 5.1 calorie. So this one is the measured value. This is a measured value. And then you compare your measured value. So measured value 5.1, true value 5 calories. Then because 5.1 is close to 5 calories, we can say that this measurement is accurate. Because it is close to the true value. But now, by some chance, if we get an average, like let's say we get an average of 3.9 calories instead of 5.1 calories, then we say this measurement is inaccurate because it is not close to the accepted value. That's the meaning of accuracy. Now, what about precision? Precision is just the agreement of experimental or measurement results. So for example, you have done a measurement, and in your measurement you find 5.1, 5.0, 5.1, 5.2, 4.9, 5.0, 5.0, 5.1. This is experiment A. Experiment B, you find 5.1, 4.2, 4.0, 5.7, 5.0, 5.9, 3.0. Now, if you look at the two experiments, experiment A and B, you will say that this one is precise because there is a good agreement among experimental values. This one is imprecise or not precise because there is a disagreement among experimental values. So what is the difference between precision and accuracy? Precision deals only with the measured values, while accuracy compared the measured values to a true value or the accepted value. So they do different things. Now let me just get rid of this ink. Now let me give these ones values A, B, C, and D. So I can show you a diagram like this one, and I want you to tell me if you are playing a dart game, what can you say about the values? So if you are playing a dart game, this part is your true value. If I average these 4 points here, 0.1, 0.2, 0.3, 0.4, if I average them, they will give me a true value. So I will say that here the result is accurate because I will get a true value if I average the points. But then the points are far away from each other. There is really no agreement between these points. So they are not precise. For B, we are saying this is the true value. And the dots here are far away from the center there. So this one is not accurate. But the values are very close together. So it is precise. It follows that C is both accurate and precise, and D inaccurate and not precise. So you can say not accurate and not precise. And based on accuracy and precision, we also define what we call errors. So errors are just the differences between measured value and what we are looking for, or the true value. We have two types of them. We have a random error. Random error is always unavoidable. We can't avoid random error. If you make a measurement, a random error goes both sides. Like if my measurement is here, this is my point measurement, a random error will show some values this side, some values this side. So measurement has equal probability of being low or high. Then we have systematic error. Systematic error just occurs one side or same direction. If my measurement is here, all my other measurement will be only this side, which means that is if this one is my true value. All the other measurements are on one side. They can be systematically low or systematically high. If we go back to our dart game, we see that we have a random error on A. So let's say A, B, C, D. So we have a random error on A, but we really don't have that systematic error because the errors are on both sides, higher and low. This one we have really a high systematic error, but low random error because the values are close. The measured values are close to each other. So the random error is very low. Here we have low random error and low systematic error. While here we have both high random error and high systematic error. So usually accuracy usually goes with the higher accuracy goes with random errors, while higher uh, precision can go with both random errors and systematic errors. But when you have high precision and low accuracy, you definitely have a systematic error in your measurement. So let's see if we can do some math using this information. So consider the measurement. Here, in your measurement, you have values. These are the given values. So if the true mass of this piece of metal is 2.586, is the measurement accurate or precise? So to answer this question, find the mean. Find the mean. And then compare the mean to the true value. So for these values here, the mean is 12.43 divided by 5, which is 2.486. 2.486. So the mean is 2.486. Now, if we look at the values again, let me just get rid of this. If we look at the values again, here the true value is 2.586. These values here do not contain the true value. The true value is systematically higher than the measured values. So the true value is systematically higher than the measured values. As a result, this measurement is not accurate because it is different. It is different from the true value. It is different from this given value. This mean here is different from the given value. So the question is, what type of error is present in this case? We have said that the true value is systematically higher than the measured value. So here we have a systematic error. So to recognize systematic error, you will see that the mean of your values will be totally different from the given value. The given value will be higher or lower than the mean, or the given value will be higher than any number present in your measurement. For example, here we have 2.586. 2.586 is higher than all these numbers, which means these values are systematically lower than 2.586. Therefore, we have a systematic error in this case. When you have random error, the value, the measured value, will always be within the values you are given. For example, here, 2.486. If we want a 2.486, 2.486 is within these values. So if our number was 2.486, then we would have said we have a random error. But in this case, our number is 2.586, which is systematically higher than all the values present here. So we have a systematic error. So check the next video, which deals with dimensional analysis. Thank you.